Hello, welcome! You're about to watch another Golan Levin guest video, and this video is all about the idea of interpolation. So Golan's going to talk you through some art history examples, which I wish I had the capacity to do myself on this channel, and maybe someday I will live up to my ambitions to do so, but which I think is going to give you a really interesting background and set up a coding challenge for you to do. I'm going to come in later in the video. There's a few sound problems when I come in because I poorly mic'd myself, so I apologize for that. You should be able to hear and understand everything, but when I enter, all the sound problems are my fault, not Golan's. But I'm going to come in and we're going to talk about this coding challenge. You're going to see a bunch of examples, and then, if you so choose, you'll be able to contribute to the repository, the code repository, and add your own version of the coding challenge. But I don't want to say anything about what it is, because I just want you to watch and enjoy. Thanks, enjoy.
Hey everyone, Golan Levin here, and by the good grace of Dan Schiffman, who's here he is, today we're going to talk about interpolation in a Coding Train special episode, which I'm first going to talk about sort of the early history of interpolation in computer graphics and computer arts with kind of a little sort of fancy introduction. All right. Who can't admire the natural poetry of the transformation of the butterfly? And yet it's hidden away inside that chrysalis. There. We want to know what's going on in there. You know, turning water into wine is a miracle, but how can we see it happen? We want to see the steps, as in this 1831 cartoon by Charles Philippon, who talks about, who uses this kind of progressive stages of interpolation to show the degradation of the king's regime. Okay, computers are the ideal tool for visualizing transformations of this sort. Here we see the covers of Animorph, right? These popular books written for tweens, which show, of course, right, you know, these characters whose bodies turn into various animals. What better time to kind of think about, you know, the transformation of the body than for tweens, right? And here we have a boy who turns into a horse, a girl who turns into a starfish, or maybe the other way around. Puberty. So there's many different words that we use for talking about interpolation. Architects call it lofting. Some people call it tweens. Some people call it interpolation or morphing. Morphing, as I know it, was as you may know it from videos and so on, was largely invented by Nancy Burson when she was an artist in residence at MIT in the late 70s and early 80s. She used it to create these beauty composites. This is the averages of Betty Davis and other movie stars of the 1950s, and averages of Diane Keaton, Brooke Shields, and others from the 70s and 80s, trying to get this kind of ideal notion of female beauty as it's understood in the popular culture by averaging together these faces and sort of seeing if maybe there's some kind of latent kind of structure there. But we really start to see interpolation start in the late 60s with early computer art. This is a project by Chuck Suri and James Schaefer, who created this progression from chaos to order. And it's a random distribution of each line of a hummingbird drawing. And we see this kind of progression from this kind of ordered situation here to a kind of chaotic one here as more and more noise is done. We see this similar project, kind of prospect of examining from order to noise in this work by Manfred Mohr called Lady Quark from 1972. In each of these squares here, a perfect square is interpolating over 23 steps to a kind of randomized polygon. And both of them have been resampled in a number of ways, and we see the kind of progression step by step by step from a square to a kind of perfect polygon. This is maybe worth trying your own hand at recreating. And the computer technique group, Masao Komura and others, in also 1968, created this series of posters in which a square interpolates not to randomness, but to another form, in this case, the ideal form of a woman's face. And there's a couple different versions of this project, one with sort of linear interpolation and one with non-linear interpolation. And that begins to get at what we're going to talk about today, like the exact character of the transformation is what we want to look at. Now, here we see this kind of transformation in terms of two endpoints that represent things we understand well, young and old. And we want to see how that happens. But unlike Nancy Burson's work of 13 years later, this project from the late 60s by Chuck Suri and James Schaefer is sort of badly defined. The lines that define one face and the other sort of interpolate from one position to the next, but without much logic, so you get this kind of glitchy situation in the middle. This is a lovely project called Fruit Salad by Hughes Crane and Adrian Hain, also from around 1970. And it's a mixture of the basic figures apple, lemon, orange, and in this case chestnut, which I guess they'll call a fruit. And they're at the corners of the design. So apple in the upper left, and lemon in the upper right, chestnut in the lower left, and orange in the lower right. And with the admixtures of these blended shapes in the middle. And this is a project by William Kolomajek from 1970 through 75, circa. Then it was, in this case, shown a few years later, where he interpolates from a banana to an ice cream cone. He says because his wife liked both. You know, the way of interpolating from a banana to an ice cream cone is maybe not so obvious, and so he's got some very strange intermediate shapes. And perhaps one of the most strange and absurd of all of these was this project called Running Cola is Africa, by, again, the Japanese computer technique group, Masao Komura and others, in which the shape of the runner from the '68 Olympics transforms into a Coca-Cola bottle and then, and then into the continent of Africa. So these kinds of complexities are a lot to deal with, and I'm very interested in interpolation. Dan, my host, has done some fantastic interpolations himself, but I want to keep it real simple. I want to say, like, what's the simplest kind of interpolation we can do? And I was very inspired by Vasily Kandinsky's book, Point and Line to Plane. He says, look, the simplest possible shapes, okay, are the primary contrasting pair of planar shapes. He says the minimally pointy and the maximally pointy, right, the circle and the triangle. Bruno Munari, again, looking at these kinds of simple shapes and saying, like, what can we do when we, like, examine these shapes? And Wuxius Wang, in the early 70s, this is hand-drawn, not with a computer, thinking about how can we interpolate from one shape to the next. So just looking at these very basic shapes, we ask, like, what are the ways we can get from one shape to the next? I particularly like this one by Wuxius Wang. Here, he has a circle that transforms to a triangle, but it looks to be almost like the silhouette of a cone in 3D. So with that, I want to show you today a kind of a coding challenge I want to pose to you. To introduce the challenge, I'm going to show you how I've interpolated from a circle to a triangle. I gave myself a week to come up with as many ways of interpolating from a circle to a triangle as I could think of. And I'm going to show them to you all with Dan at my side. There's a lot of ways of getting from A to B. And John Cage once said, if something is boring for 2 minutes, do it for 4. If it's boring for 4 minutes, do it for 8. Boring for 8 minutes, do it for 16, and then 32, and eventually you discover it's not so boring after all. So we're going to go through all of the ways that I could think of in a week, and then we're going to invite you to make more of your own and kind of think of all the different ways that you can think of to interpolate from a circle to a triangle, and hopefully get your contributions onto our GitHub repo. So before we really get started, I want to talk about maybe the understructure of the constraints of the problem that I'm going to pose to you guys, and how I've made my 13 or 14 different solutions. What's our goal? We want to get from a circle to a triangle, right? We want to interpolate. And the question is, how do we want to get there? And there's so many different ways. And there's no one correct answer. But a lot of the solutions that I'm going to show you that I've come up with involve subdividing these into multiple points, sometimes maybe 100 or 300 points, so that we have more stuff to play with. So what's really happening? Well, I'll have a circle, for example. And I'll have a triangle that looks something like this. It's an equilateral triangle, right? Although maybe I didn't quite draw it like that. And then they're going to share 3 points. There's a point here, there's a point here, there's a point here that's shared by the triangle. But what I've done is I'm actually subdividing secretly the circle into lots of little pieces like this. And so there's little particles or pieces that go around the circle and so forth. And there are matching or corresponding points on the perimeter of the triangle that match these, like this. So there's points along the triangle that match these points. And so, for example, in the very first transformation that I'm going to show you, I'm going to do the very simplest thing. I'm just going to move each of these points in towards its corresponding point. I'm going to say take this and move it towards this one move it towards this one move it towards this one towards here, this one towards here, and then keep going, right? So that's going to be the first transformation. We'll talk about all the different kinds of other transformations. We'll see there's actually a lot of different ways. All of the different circles and triangles I'm showing you consist of some kind of perimeter that's been computed, okay? And in no cases are there any sort of tricks where I'm pasting like a white circle on top of a black circle, right? There's a computed perimeter, and I'm drawing it with, I think, a 6 pixel thick or 3 pixel thick line. All right, let's go over here. Dan, you want to join me?
Yes.
Awesome.
Yes. Oop.
Okay.
We're both here now. First of all, thank you for tolerating the fact that apparently this studio is made for a right-handed person.
I'm a lefty.
I didn't realize that till today.
I'm thrilled to be here.
Yeah.
Thank you so much for having me.
No, this is awesome.
So I thought I would show you some of the things I came up with. All right, and I guess this is your first time seeing them, right? So
yes.
Yeah. So we're gonna do some surprises for Dan here.
Okay.
I'm gonna show them out of order. I have a GitHub repo where they're actually stored. They're over here on my GitHub. It's
well, that'll be in the video. The link in the video's description.
Oh, well, okay, excellent. Yeah. So there's a GitHub repo, but I'm going to show them out of order rather than the order I made them in. I'm going to show them in maybe an order that kind of introduces the concept better. So this is the first one I want to show you, Dan.
Okay.
And in this one here, okay, it's just as I explained over there on the whiteboard. I've resampled the circle and I've subsampled the triangle into the same number of points, and I'm moving each point from the perimeter of the circle into its corresponding place in the triangle.
Right.
In a linear interpolation.
And are you actually using the Lerp function that's part of P5, or did you write like that
I probably am using the Lerp
Yeah.
function. If I'm not, I probably should have. Both are good. I mean, the Lerp function, it's not too hard to make yourself,
Right.
actually.
It's one line of code, actually, if you look at this.
So I might be doing that, but that's what's happening here. Those points are moving in from the circle to the triangle along this kind of ray. And those rays, in this case, actually, those rays don't actually correspond to the radii of the circle. So there might be some weird angles in there where they're moving in strange directions. Right. The next one I want to show you, okay, is instead of moving those points in linearly, I want to basically on every frame of animation, I nudge them in by a random amount. Okay, and then I connect them with a Bezier so it looks smooth instead of jaggy.
Oh.
Okay, so that's number 5. Okay, so I'm going to go over here.
I pretend to watch it over here, but actually I have to look over here.
No, it's fine. So if we look there, you'll see that each of those points is gradually moving in towards the corresponding point. And then at the very end, I do a computation to see how different they are from where they should be, and I flip it back. But there's a challenge left to the reader, which is to figure out how to move it back from a triangle to a circle. I didn't do that.
But wait, so you said, so I totally get this in my head.
Right.
But what I don't get is how the Bezier plays a role here. What does that do exactly, and how do you? What's different about just drawing? Because you must be using begin shape and end shape and setting all these points. So,
yeah, but I wanted it to look smooth.
Right.
And if I hadn't used the Bezier, then it would be zigzaggy.
Got it.
Which is fine. That's legit.
Yeah.
That's another way of doing it.
Right.
But I wanted the only sharp vertices. This was an artistic choice to be at the corners where the triangle was. Yeah, exactly.
It almost looks like you're using something like Perlin noise or something because of the way the smooth contours are, but it's just randomness.
I don't remember.
I'll have to look in the GitHub repo. You'll find out.
Yeah.
Or try it both ways yourself.
Now I'm going to show you another one now, and it actually it ends up in a very different situation. And it looks really similar to the first one I showed you, which is number 4 technically. Okay, but it's a different way of doing it.
I love all these like little surprises here.
Yeah, little surprises. Now this one is number 0. Okay, and if we look at this one here, okay, check this one out. You may think like, what's the big deal? It's like just moving really slowly. Okay.
Yeah.
Now this one takes a little bit of knowledge about signal processing. Okay. What I'm doing is the following. I take the circle, and I subsample it into all the different points in the circle. I've got maybe, I don't know, a couple hundred points around the circle. And then I locally average every point with its neighbors. Okay? So that basically each one is moving towards its neighbors, and it's tightening up the ropes with the exception of 3 points that are fixed. So I fix point, and I say those points cannot move. Every other point can move. Right? So when
So it's like a blur. You're basically blurring the circle into a triangle.
Right, exactly. I'm blurring the circle into a triangle, but I'm fixing 3 points and say those points can't move.
Yeah.
Right? If I didn't fix those points, then the whole thing would shrink.
And if you want this perfect equilateral triangle, but if you picked 3 random points, it would probably shrink into
different
that.
way. That's right.
That's
exactly.
interesting.
Yeah.
Somebody should try that.
Okay, now we're going to move on. I've shown those 3. So let's begin with some easy ones here, okay? Here. Now this one, what's this one here?
Ooh. Ooh.
Okay. Okay. So
whoa.
Okay. In this one, want to guess what's happening?
Well, you must be doing 1 point at a time.
Yeah. So exactly what's happening here? I start with a circle.
Yeah.
And I'm going to and I have the circle is subsampled into lots of points that are stored in an array. Okay. And
so each of your examples, it's not necessarily always just 200 points. Some of them have like 2,000, some have 200, or all the same number of points. We don't know. We have to look to find out.
It's been a little while.
Okay.
But it actually sort of depends on the example.
Yeah, that's what I mean.
It
So
depends on the example,
it's not necessarily like that's not a design constraint that you're saying to yourself,
right.
like, I wanted to do this with just this number of points.
You know, the funny thing about a circle anyway, Dan, right, is that actually it's a polygon.
Right.
On a computer, you know, like it's just a polygon with a lot of sides.
Yes.
Right. So in this case here, I have a polygon with a lot of sides, which we'll nickname a circle.
Right.
And then I use some of the great operators.
I just hear you're deleting them one at a time.
Yeah, I'm actually deleting the data in here. So I selectively delete all the points off this array.
Oh, of course.
All points but 3. I delete all the points but 3, and that's what this is.
Because I'm sillily in my mind like interpolating each point one at a time to the spot in the triangle,
I'm just
which would be a ridiculous way of doing
deleting
it.
them.
Yeah.
Because actually JavaScript has some really nice ways of playing with splice and delete and these kinds of other ways of like playing with arrays where you like literally delete data. But I stash a copy off to the side so that after it's done with its operation, I refresh it with the original copy. So that's number. Let's do number 7 now. Okay.
Whoa.
All right. This one's easy. You want to describe it?
Well, now you're adding more points.
This one only does it go both directions? Yeah, it does. Right, exactly. So this one says, well, you know, really, there's a way that they say to make a sculpture of an elephant. Okay, you start with a block of marble, and you remove all the pieces of the marble that don't look like an elephant.
Right.
Right. So that's what's going on here. I start with the circle.
Oh, it started as a circle. I somehow turned to look at the right at this part here. Okay.
Right. Now it starts as a circle.
Yeah.
And I remove all the points of the circle that don't look like a circle. The triangle, and then I end up with the triangle. So boom, voila, triangle.
Yeah.
Yeah. Okay. That's number 7. Number 13. We're gonna do. Okay. What's going on here, Dan?
So well, you go from a triangle to a
hexagon
to a whatever
dodecagon.
Gon,
not hedron.
Hedron. No, gon.
Gon is polygon. Hedron is faces, so solid.
Okay. Solid. Yeah.
Solid model. So yeah, this basically says start with 3, double it, get 6, double it, get 12, double it, get.
And you just decide at 128 or whatever the number is. It's not 128, but it's some number you stop.
Yeah, 48 or 96 or something like that, and it looks sufficiently like a circle at that point. And there's a little bit of nonlinear interpolation in terms of the way that it moves from one point to the other to kind of give it a kind of acceleration, but that's just a grace note.
Right.
That's just not actually necessary. All right. So that's there. Let's move on to number 2. O2. All right. This one I think a lot of Illustrator users and graphic designers will recognize. Right. What's your
Bezier curves again?
That's right, Bezier curves again. So what's interesting is this, okay? When this one gets up to looking like a circle, it's not actually a circle, but there are some magic numbers that you can Google around and find, which define the locations of
the control points.
These control points here, these control points that define
a perfect arc,
a very close approximation. Yeah. Good enough for government work for a circle with Bezier curves. It's not a true circle, but it's 3 Beziers that with the magic control numbers look very close to a circle. And so here, what I'm doing is I'm moving those control points until they're so close together that they essentially create a sharp vertex, and it's a triangle. Yeah. All right. That's number 2. Number 3 over here. What do you think of this one?
Whoa. Let's see. Hold on.
Yeah, I have a couple guidelines in there to help things out.
I mean, what's interesting to me is this looks just almost exactly like the first one that you proposed, where each point is moving from the circle to the triangle. Like visually, it feels like it has the same result.
That's fair. That's fair. It's not what's happening, though.
But that's not what's happening.
No. Okay. So in this case here, the graphic as a whole, there's no subsampling at all. In fact, there's only 3 graphical elements that are, apart from the red lines, which are the guidelines to kind of help you understand what's going on, there are only 3 graphical elements, okay? The entire thing is always drawn with 3 circular arcs. The difference is that the circular arcs, their radii goes from the radius of the circle to infinity.
Infinity.
And when you have a circular arc whose radius is infinity,
straight line.
You end up with effectively a straight line, which is what the triangle is made of.
Yeah.
Right. So those you can see the vertices of the triangle heading off to so the corners where the arc are defined from heading off to infinity. And when that happens, you have this triangle.
It feels like breathing. It'll be good for like meditation or something.
It's a venerable form. All right, let's try another one. That was 03. So let's move on to 06.
What's the original numbering? Just the numbering that you happen to do them in?
Yeah, that's right. Yeah, exactly. Okay. This one I think is almost like as pretty as a logo, right? Got kind of like a logo graphic.
Oh yeah, I think there's like Airbnb is in there somewhere. I by accident buzz marketed something. Let's cut that out.
But it does look a bit like a logo.
Yeah.
This one's very simple. What do you think is going on here?
Let's see. Well, are you doing the same thing, but with curved vertex, of adding or removing points, but with curved vertex?
No. It turns out that what's going on here, the math to do this one's a little bit fussy. This is an alternation of 3 circular arcs and 3 straight lines. The straight lines are actually accomplished just by I draw a vertex
at the end of the arc,
and then I draw another set of vertices, another set of vertices.
So you can't use the actual arc function for here, which you have to calculate that arc, so that you know where the endpoints are.
I probably could.
You could, but you still have to calculate the endpoints for the line.
Well, so that would have been a different way of doing it.
Right.
Right. So what Dan's just said is, I could have done this by drawing an arc, drawing a line, drawing an arc, drawing a line, drawing an arc, drawing a line. But I didn't do it that way because I set the personal rule for myself, and I invite you to have the same rule, which is that the whole thing is computed as a single perimeter. So I've computed every point along this perimeter. And to do that, I had to compute using sine and cosine. I'm sure you could.
Yeah. There's a video tutorial for that. I'm trying to include it in this video's description as well.
But yeah, I compute all the points along the circular arc. Then I compute all the points along this circular arc, and on the third one, and the begin shape, end shape takes care of the rest and stitches it all together and creates the straight lines in between.
Right. Got it.
And that was number 6. Here's number 12. Let's have a look here. All right. Now, there's some guidelines here as well you can see on this one. You want to guess what's going on here?
Well, now this is how I imagined you did the previous one. Oh, except that the line, there's some other circles there.
Yeah. Okay. So this one is the alternation of, there's 6 circular arcs. Okay. Let's call them type A and type B.
Okay.
Okay. Now the type A are simple to explain. They're corners.
Right.
Okay. So the corners are circular arcs.
Got it.
And they change from the radius of the circle down to 0.
Yeah.
Okay. So they get from the radius of the circle down to kind of pointy.
Right.
Okay, but the B-type arcs are alternating, so it goes A, B, A, B, A, B around the circle. Right. And the B-type arcs start at the radius of the circle, but go out to infinity.
Right.
And so they get larger and larger, and therefore straighter and straighter.
And so this is exactly the same as the previous one, except for instead of that straight line, there's the B-type arc. Is that right? Maybe not.
Maybe.
Close enough. We could cut that out too.
All right. That's 12. Next, I gotta confess, Dan, the last ones are really ugly.
Okay, that's good. Ugly is good.
They're like these are like, I wouldn't call them the rejects, but like they're.
One of the things I like to do with this channel is to make ugly stuff, and then have the world out there of people who are talented at making beautiful stuff make it beautiful. So somebody will figure out how to make the ugly stuff turn beautiful.
These are gnarly. All right, number 8. These are the least loved. Okay. Oh, so gross, but very simple. You just push in on the circle till you get a triangle, right? But again, it's a computed perimeter. So, so there's an arc that's computed, and then I just draw a straight line. But I don't make any attempts to kind of negotiate that change in curvature there. Right. I just basically like, it's just cropping in. Right. But notice I'm not doing this by like moving in some white rectangles or anything like that. It's a computed perimeter. All right. Okay, number 9. I think this might be the ugliest of the bunch. Maybe.
It is kind of ugly.
Thanks. It is, right? The circle shrinks, revealing a triangle.
Got it.
Yeah, exactly. Gnarly. All right, number 10 is for you physics enthusiasts out there, I think. Yeah, this is the one.
Whoa. Like a little sine wave or something?
No sine wave. Springs.
Springs, of course. Oh, I like that.
Of course.
Yeah.
Right, exactly. So
that was kind of the same thing.
So I think I got two different sets of rest lengths and or rest positions, and then they basically they go doing, and then they get attracted to their other set of rest positions, doing, and they kind of move from one to the other. So there's a bit of slosh, and then when it gets close enough, it sort of flips and goes to the back of the other set. So there's that one, and the last one I have today, Dan, is number 11. And this one was started as a bug.
Whoa.
Yeah, I can't even explain this one. To put words to this, I mean, I can't even quite describe it. This was actually a failed attempt to produce one of the other ideas. And along the way, I just kind of had this happy accident.
Yeah.
And I was like, oh, like, I would never have thought of this. It was a complete happy accident. Yeah, right.
It's well, to me, if I were to explain this, it's each side is subdivided into straight line and arc, and the arc is and
shrinking or increasing.
Is shrinking or increasing, and I guess the radius for that arc, the center point of that arc is moving, which causes something's happening with the radius of that arc too. It's not just like a bubble.
I had like an off by one error with one of the other designs, and that's how this one happened. Yeah. Actually, it was the one that looked like a logo.
Right.
This was a failed attempt to make the one that looked like a logo, and that's how it happened there. So I thought it'd be fun to kind of open this up for everyone else.
Yeah.
Oh, and I have one other special treat, which is to say I also have all the same things for squares.
So square to circle.
Square to circle.
Not square to triangle.
Well, you could
do that.
You
could do circle to square to triangle.
That's right. Now, I did, in fact, many of these transformations, I simply copied the transformation and, I just added a fourth side. So those exist. So if you prefer squares to triangles, and I actually kind of do myself, and I wouldn't blame you if you did, because triangles are so pointy, and you're like, ouch, I don't want to deal with those points, you can do this with squares instead.
So there's a GitHub repo.
Yes.
Which has all these examples.
You bet.
And we're just sort of coming up with this right now. So people could submit theirs a variety of different ways. One is, these are so conducive to making a nice little GIF. You could tweet the GIF maybe with like a hashtag.
Tweet the GIF, that's right. What should you tweet them to coding?
Well, sometimes we use the 10 print hashtag, or so maybe triangle circle.
Triangle circle.
Triangle circle. Then you can also we could create like a markdown file in the GitHub repo where people could link to theirs, or they could just pull request the actual code into it.
So
we'll write up some instructions or something on the repo.
Sounds great.
And I think what would be fun, for me at least, is to try to either come up with my own or just remake one of these as a little tutorial. So if people want to get started at some point, it might already exist by the time that you're watching this, but there'll be a follow-up video that'll be linked to of me kind of going through and making one of these.
That's right.
Okay.
Actually, Dan, you already have made one of these.
It was a failed one, though. I think I didn't.
No, it was not failed. It was not failed. I actually have a link, and if I just show you for a second, over here in my repo, I linked to the one that Dan made. It was the one where you were using super ellipses to morph from a circle to a square.
Oh.
So it was.
I did something more complicated by accident.
Not only that, he's actually done it twice. Okay, he's forgotten. He has a 10-minute coding challenge on shape morphing, and another one, a coding challenge number 19 on a super ellipse, which is specifically for circles to squares. And does not work for triangles. Okay.
So that one, you're pointing to the time code in the video?
Yeah.
So this one I felt was such a disaster that I never actually edited it out as a separate coding challenge video. So maybe I'll redo that one, or I'll just revisit it to see if we can put it somewhere. But yes, you got the link right there.
And if you like this stuff, I also have some more links over here in the GitHub repo, just for more references and things.
Awesome. Cool. Great. Thank you so much for being here. This is thrilling and exciting.
Such a pleasure and honor.
Did you actually make it all the way to the end of this video? Thank you so much for watching. Now, if you made it all the way to this end of this video, there's actually a really special treat in store for you after you listen to me talk for about 30 seconds. I'll get to what that is in a second. So I just wanted to come back and say, here's the GitHub repository, GitHub/Golan Levin/circle-morphing. I will put a link in the video's description. All of the code examples are here, and we'll come up with a way that maybe you can submit a link to. Maybe there's a way that you could just even add yours to this README. But if you want to share yours, make an animated GIF of it and add it to Twitter with the hashtag circle morphing. Since there's no results for circle morphing, I look forward to many results for circle morphing. And it could be circle to triangle or circle to square or whatever you so choose. So let's use that hashtag. Let's use this repository. And at some point, you'll see a video from me where I actually go through one of these and do a little tutorial about it as well. OK, so you watch this whole video and you watch this extra explanation from me. Now you will get to see Golan Levin reading from what I hope will be a new tradition for all Coding Train guests, reading from the Book of Random Numbers, the Coding Train storybook. Good night, even though it might not be the night, but sleep tight and listen to the nice lullaby. Goodbye.
I'm going to read line 09505. 09505. 03003. 02041. 43212. 10780. 84788. 68377. 59637. 41731. 97081. 88146. Thank you.
Perfect.